are there any questions?
Yes.
Okay.
So on the practice exam, numbers 11 and 12, the questions are for the reaction zinc plus copper 2 plus goes to zinc 2 plus and copper solid, circle all suitable cathodes, and then for the next one is to circle all the suitable anodes.
Well, anyway, that particular one has this. This is Zn2 plus 2 electrons. Oxidation half, and then we have the reduction half over here. And so the oxidation is the anode or the cathode? The anode. And so we have this as the anode. And then over here we have this as the cathode. And so for the cathode, we have some choices we can do. And what are the choices on the list?
Zinc, metal, apparently, copper, metal.
Okay, wait, stop at zinc. We can't use zinc. The reason we can't use zinc is because yeah, we can't use zinc because if we just add zinc, or if we use zinc here, then copper 2 will take the electrons directly from the zinc, bypassing the external circuit, the wire. So we aren't going to pull any electrons through the wire, we're just going to pull them directly off the zinc metal. And so zinc is not acceptable. What's the next choice? Copper solid. Copper solid is fine because copper solid will not be oxidized by copper 2. And so that's no problem. And copper solid will supply electrons to the copper 2. And so we just need something to feed the electrons to copper 2 that won't react with copper 2. Zinc is not good, but copper is okay. What else?
Next one is platinum.
Platinum. Platinum is fine too. It's just that platinum is expensive, so don't use it. And the other thing is, you're going to be plating, although it doesn't look like plating, you're going to be plating copper metal on the electrode. So it's nicer to plate copper metal on copper rather than copper metal on platinum. You know, but it doesn't matter. I mean, you could scrape it off, but if you scrape it off, you don't want to scrape off your platinum in addition to the copper, right? So you be careful. And you wouldn't want to be sanding platinum because you could sand off a couple of $100 worth of platinum like that. It's not worth it. Right? But you could dip it, you know, if you had trouble getting the copper off the platinum, you could just dip it in an oxidizing acid. What acid would oxidize copper metal? Nitric. Yeah, nitric acid's a good choice. Yeah. Well, strong oxidizer, you should say. Because acid, you know, HCl is a strong acid, but it's not going to touch copper. All right, so platinum would work. What else? Magnesium. What do you think about magnesium? Is magnesium good? Yeah, what's the oxidation potential for magnesium? Oh, it's very high actually, plus 2.356. Very high. It's even higher than zinc. Zinc is only 0.7. This is 2.35, which means that it's even more reactive than zinc. So if you had a competition between pulling electrons off zinc versus pulling electrons off magnesium, you'll pull all the electrons off magnesium, completely bypassing the external circuit. Okay.
Graphite?
The graphite's the next one. Okay, graphite. What do you think about graphite? Graphite's good. Graphite's good. Graphite's hard to oxidize. In fact, you know, graphite, you can't melt the stuff. Have you ever seen anybody heat graphite? Yeah, if you try to melt it, maybe, wow, this, I haven't seen this. It's 4 minutes, it's too long. It's fast forward. So he has a structure of graphite there. Oh, actually, he's heating it electrically. I want to see someone with a torch. It's all right. This is a piece of wood, so
Wood's gonna burn off the outside.
yeah, it's just gonna burn off the outside. There's nothing special. Well, anyway, the point is that you know, you try to melt the stuff, it doesn't melt. It'll start vaporizing the graphite. It gets red hot.
But it doesn't burn.
Yeah, it'll oxidize, you know, slowly to carbon monoxide, carbon dioxide. Doesn't have a melting point. You're not going to melt it. Let's see. Well, let's see what Wikipedia says about the melting point.
Or the vaporization.
It's a naturally occurring thing.
Yeah. They don't, it's a refract, you know what a refractory material is? It's a refractory material. And refractory materials just don't burn. They're like ceramics are refractory materials. So they can take a lot of heat. So, a graphite crucible used to hold molten metal. They don't give them any kind of melting point here. It's not gonna melt. Okay, what was the next one? You guys did this, copper and graphite. Oh, that was it for the list?
Yes.
Okay, all right, then.
Next one is suitable anodes, and the choices are the same.
The choices are the same. Well, you have a choice. You could have a, you know, you could do what's called, you know, kill two birds with one stone kind of thing, and that is, you could just make the anode out of zinc. If you make the anode out of zinc, then the zinc is going to come off the anode and supply the electrons into the circuit. But you don't have to make the anode out of zinc. You know, the anode, it just has to be some electrical conductor.
Does it have to be an electrical conductor other than copper for this situation?
Does it have to be an electrical? No, it could be copper.
Can be copper.
Yeah, it can be copper. Right, because the copper is not going to be attacked by the Zn2 plus, so we can make it copper. But the problem is if we make it copper, then what we have to do is we have to figure out a way to detach the zinc. You know? And so what we'll do is maybe we'll wrap some zinc foil around this. But then if we wrap some zinc foil around it, it's the same thing because this is electrical contact, and the wire that we use is copper here. So this is just an extension of the copper wire. Yes. So let's say you're running low on zinc, you could do that. You don't have to have a big chunk of zinc. You could just use some copper, wrap some zinc around it, and then whichever has a higher oxidation potential, whichever has the highest oxidation potential will be oxidized. So zinc is going to be oxidized before copper. And then, so whatever we use for the electrode, it has to be in contact. We cannot use magnesium. But that particular question can have multiple answers. One, you just say zinc, it's zinc's anode. Two, you would have to say zinc attached. Like, for example, if you said copper, there's got to be some zinc in there, and so you'd have to say copper and zinc. If you just said copper alone, it's not going to work. You just dip it into a zinc 2+ solution, and so technically, it's only zinc that works.
Platinum.
Yeah, platinum you could use. I mean, but for that particular answer, I was looking for zinc, just zinc.
We'll go over a problem number.
All right.
19D, part D. The cell diagram was kind of weird.
Okay, let's take a look at that. Okay, 19D.
Starting point.
Do you know what page it's on?
908.
Oh, okay. We just got there. 19D?
Yeah.
Let's take a look at that. Platinum. So here the electrode is platinum. Platinum is very unreactive, so it's a very popular electrode material. But with some researchers at the University of Michigan, they were trying to see if electric and magnetic fields affected cancer cell growth. And so they stuck a couple of platinum electrodes in a petri dish full of cancer cells. And they noticed that the platinum started to react with the material inside the petri dish. And whatever the product of the reaction was killed all the cancer cells. And so they thought, wow, this could be a good chemotherapy agent, like a chemical toxin for cancer cells. And so they had this mixture, but how do you isolate? How do you isolate and then determine what that compound is in such a complex mixture. And so this is what, you know, chapter 1 was all about. Chapter 1 is you use physical and chemical properties to separate things. But you know how much product was generated? Minimal amounts of product, right? And so by the time you finish separations, you lose a little bit here, lose a little bit here, lose a little bit here. By the time you get to the end, you just have a few molecules worth, nothing you can do anything with, you know. That's an exaggeration, but you know, it's easy to not be able to isolate any of the active ingredient because there's so little. And so since it was so hard to separate and isolate the active compound or active compounds, it could be a mixture of things. They started guessing. And so what they did was they looked in the book and figured out all the platinum compounds that were around and then figured out what was in the mixture and then tried each and every one of those. And you know what? It was a compound that's been synthesized before and isolated. And it turned out it's called cisplatin. And it's a cisplatin. If you read it, you know, it's a pretty interesting story. And actually, the drug was made, one of the most successful chemotherapy drugs available. Cisplatin is square planar. Cis means together, and so it's a dichlorodimine, like this. The transplatin doesn't work. Only cisplatin works. And they think cisplatin works because this gets wedged into a groove in the DNA, whereas the transplatin wouldn't get wedged into a groove in the DNA or whatever, RNA. And so that's it. The person who discovered it became immensely rich from that discovery. It was very expensive. Yeah. So there's a story about that. Anyway, so platinum is the material of choice. It usually doesn't react, but in that case it reacted, which is very unusual, right? But here we'll just use some platinum. Here. And then this is, I see, it goes from O2 to H plus to OH minus to O2. So this is the weird part here.
Yeah.
What's going on?
Yeah.
Yeah, what kind of couple is that? O2 to H plus. That's a very odd couple, isn't that? It's a very odd couple. And so let's see if we can figure it out. And so we have to bubble O2 gas in here. O2 gas. And then there's going to be some H plus in here. H plus. Now, they're asking us to use data from table 20.1 to calculate E naught of the cell for this. And so if we look for O2H plus, this is one way you could do it.
There's only 3.
Yeah, let's take a look. All right, we have, actually, is this the, you know, on the left, is that the anode or the cathode? Anode. And so the anode is where electrons are generated, right? Because electrons are generated, they're going to be fed to the cathode. And so what type of reaction are we looking at for at the anode? Oxidation or reduction? Oxidation. So we're looking for an oxidation half reaction that has, well, the oxidation half reactions are reversed. So we need O2 on the left and H plus on the right. So let's see if we can find that. So here's an O2. O2 going to O3, ozone. There wasn't any ozone in there. We shouldn't use that. There's that. We go down. This. Here again, we have O2 goes to ozone. but this is in basic solution. And so it looks like the only choice we have is this. O2 goes to ozone in acidic solution. But the problem is why didn't they write ozone in the cell diagram? You know, there should be H plus and ozone on the right. You know, but they did it on this other one. For example, here, you know, actually they didn't do that. And so O2 goes to H plus. Well, the only option is if there's ozone in there. And then this is, yeah, this is hydroxide, O2.
They did something really weird for their oxidation. They put water, goes to oxygen and H plus.
Oh, okay. All right.
And for the reduction, they did oxygen plus water, goes to hydroxide. Which I don't know why.
Okay.
The hydroxide is on the left side.
Okay. Yeah.
Is it a typo?
Well, it's a bit weird. You know, that one, you know, I guess somebody could argue that it's okay because water is a pure liquid and water is a solvent. But then again, you know, platinum is just an inert electrode. And so, you know, it's weird because you would want to state something like this. H2O liquid, right? The O2 gas, the H plus AQ. Then that would make sense because then we'd have water being oxidized. Water is being oxidized to form this. And the half reaction would be okay. But it's a little weird because here they state platinum, but they don't state the water, and they might argue that, hey, you know, water is not necessary to state. You know, this bar doesn't necessarily mean, you know, reactant product. The bar usually just means change or difference in state. And so here they're just showing the products. But it's not a proper couple. And so if you're looking for the couple, the O2H plus couple, it doesn't exactly come to mind because normally you think O2 is oxidized. And so,
So it's just a different notation?
yeah, I wouldn't worry about it. This is I guess this is a trick question.
Is your preferred notation just the usual thing being oxidized? So the thing being oxidized on the left?
Right. Because there, I mean, you would do the activity. The activity of H2O liquid is 1 anyway. They're just going ahead and substituting that in there as 1. You know, then the activity of O2 would just be the pressure of the O2, and the activity of H plus would be the concentration. But my preferred notation is when you have a couple, you have the reactant and the major product, right? In fact, my couple, I wouldn't even bother with the H plus unless if it's under standard conditions, I wouldn't even bother. My couple would be H2O goes to O2, the major product. Because nothing happens to H plus. The H plus is +1 here, H plus is +1 here. And so in that sense, this is the spectator. Well, let's get rid of that and then have H2O goes to O2. This is my preferred, and this is the way I would have written it. H2O liquid goes to O2. Yeah, H2O has 2 couples. H2O goes to O2 or H2O goes to H plus. Not H plus, sorry, H2. And so this would be an oxidation of water, this would be the reduction of water. You know? Those are the 2 water couples I know. And so that's a weird problem I wouldn't even worry about. In fact, I would put this on the homework maybe just so you've seen something weird like this, but otherwise you can just erase it from your memory. So, I mean, you might dredge it up from your memory, but it's this is a very odd couple, O2H+. All right, was there any other questions in the homework? I wonder if they show that. You see, they're not even being consistent. So take a look. Look at this couple here. This is the H2O-O2 couple, just reversed. It's O2 H2O, right? And so they aren't even being consistent with their own notation, but that makes sense because there's so many authors in this book that each of them has their own peculiar way of writing it. But I would say the text is, I would say that is, you know, so I could see somebody arguing that, oh yeah, it makes perfect sense, but you know, it doesn't.
There was another one that I can't find right now.
Look at this. Oh, sorry. But well, look at this. H2O H2 couple. No. So I would just go with, yeah, whoever did that one. I forgot that.
There was another one that I think that their notation was instead of writing 2 bars in the middle, I think they took the salt bridge like explicitly. So they put like potassium.
Yeah. Yeah, that's okay because that's an okay method because that is the salt is very specific. It has to be a alkali hydroxide. It has to be a hydroxide salt. Because if you didn't have a hydroxide salt, then it's going to change. Yeah, because that's the case when the salt in the salt bridge is a reactant or reactive species as well. It's just weird because in that particular reaction, it's produced at one electrode but consumed at the other, so the concentration stays constant because as soon as it's produced, it's consumed at the other. Yeah, it's an intermediate. It's important to have that, otherwise the reaction doesn't occur.
And as far as the formal report, I was going to ask you, when's the due date? Or can we do like last semester where we turned it in after?
Yeah. Yeah, the formal report we can turn in after the final, we do. And so it could either be due Friday, like Friday afternoon, or Monday. Okay. All right, well, the formal report can be due, but you can turn it in early if you want. But we'll have the hard deadline Monday. Before the office closes. I need a hard copy. I don't want an electronic copy. One semester I got an electronic copy, I couldn't open it, the file. And the person already took off out of the country or something, couldn't respond to any emails or anything. Another one, I don't know, they sent me like 6 files, you know, 1 file for this figure, 1 file for that figure, and then it was all, you know, mixed up, and it wasn't even like a cohesive paper. Yeah. Not that a printed out version would. The other one, I'm going to give you back your formal report, the one tomorrow. Back to you now. We can talk about it then. Okay. All right, are there any other questions? Yes? No? All right, we're going to continue with chapter 24. Let's see. No other questions on chapter 20? Or chapter 24, there are two main topics we're covering in the last part here. One is isomers. The other is something called crystal field theory, which tries to describe the magnetic and optical properties in color. And so going back to the first half, we were just looking at naming these things. Nomenclature. Okay, in the second half, we talk about isomers. There are subcategories of isomers. There's something called structural isomers. Structural isomers where you have totally different bonding skeleton or different bonding arrangement. And so, an example of that would be SCN or N. Wait, SCN. What would be another one? SNC, something like that. Where they're linked totally differently. This would be an example of structural isomer, where the bonds are different. But a stereoisomer is where the bonds are all the same, except they're just arranged differently in space. How so ionization isomer would be the structural isomer. You don't have to memorize ionization isomer because it's rarely used. These are just two isomers. People would just say these are two isomers. In this case, the amines or ligands here. The chloro is a counterion. Over here we have amines as ligands as well. But if you look, the chloro is now inside the coordination sphere. And so this has a sulfato. And if we change the position here, then that's going to totally change the bonding arrangement. So there's going to be 6 bonds to the chromium. And so we can see different bonding arrangement, the structural isomer. But we don't have to call it ionization. These are structural isomers as well. Because over here we have the hexamine cobalt with the hexacyanochromate. Over here it's hexamine chromium with the hexacyano. The parentheses are missing there. Do you see the parentheses are missing? This is not 6 nitrogens and 1 carbon. This is supposed to be 6 cyanos. So they forgot the parentheses on this slides. And I didn't fix them. I just posted these as given. I didn't make these slides, the textbook. But anyway, the hexacyanocobalt. So you can see the cobalt and chromium switch because it's a structural isomer because of different bonds, right? Structural isomers, structural isomers. If you want to get all fancy, then you can come up with all these little names here, but nobody uses these little names: coordination, ionization, etc. Unless you're really a specialist in this. Linkage is another example of structural isomerism because in a linkage isomer, if you look at the nitro group here, the nitro is attached with nitrogen. Here we have a nitro attached with the oxygen. So we call this nitrito O or nitro O N, and nitro O. Remember that with the hyphen? But these are structural isomers because the bonds are totally different. This bond's totally different. This is a green-blue bond. This is a green-red bond. Totally different structural isomer. And so structural isomers, you just figure out, are there different bonding arrangements? Okay, this is a geometric isomer. The geometric isomer is the bonds are all the same. We have 2 gray greens and 2 gray blues. In other words, we have 2 amines and 2 chloros. This is cisplatin. This is transplatin. Here. You see the structural difference. This is structural isomers. Are they structural? No, these are not structural isomers because structural isomers would have different bonds. These are what we call stereoisomers or geometric. Stereoisomer is a very broad term. These are geometric isomers here, cis-trans, geometric isomers. There are 2 more geometric isomers that I didn't even get to yesterday. They're the mirror face but we'll do that. Cis-trans can occur for both square planar and octahedral. Like for example here, you know, when you did the oxalato, you could put the, what was it, the chlorose cis, or you could put the chlorose trans, right? Now, for tetrahedral complexes, is there such thing as cis-trans isomerism in tetrahedral complexes? No, because all the positions in a tetrahedron are adjacent to each other. There's no such thing as opposite in tetrahedral. Because the bond angles are all the same, right? Because of the symmetry. It's what we call spherical symmetry. Have you heard of spherical symmetry? Tetrahedral spherical symmetry. All right, so we have cis-trans. Now, we have potential for other isomers. What are the potential for other isomers for each of these? The potential is this. What we do is we take this isomer, the cis, and pretend there's a mirror here and construct its mirror image. And then see, will that mirror image superimpose on the original? And if you do this mentally in your head, if you made the mirror image here and just flip it, you know, over on top of it, it superimposes. And so we call this not optically active. The cis isomer is not optically active. How about the trans isomer? If you make a mirror image of this, it's not optically active because it's superimposable, right? There's another way of determining if something's optically active. If something's optically active, we can, you know, there's a mirror plane here, but what we could do is we could try to slice the molecule in half. Or pretend we can cut the atoms in half too. And so we slice it right down the middle. Do we get two even halves?
Yes.
Yeah, that's called a mirror plane inside the molecule. If the molecule has a mirror plane, it cannot be optically active. You know, so if something's optically active, no matter how you slice it, you'll never get two even halves. You'll always get asymmetric halves. It lacks a mirror plane of symmetry. And so we could see, you know, is the cis form of this optically active? Well, two ways. We can draw out its mirror image and then see if it superimposes, or we could try to slice it in half. And is there a way to slice this in half so that you get two even halves? Actually, there are. There are two mirrors. One horizontally, right down the equatorial plane, and cutting right between the two chloros and right between these two amines. Just slice it in half. You get two even halves. So there are two mirror planes here. Boom, boom. So this is not optically active. How about this? Is this optically active? No, this is not optically active either because we could just slice it down the chloro here or down the amines. We get two even halves, right? And so there are only two isomers for this, and that's a cis-trans isomer for this. Okay, we have, well, what happens if you have three of a kind? If you have three of a kind, then we can have the facial isomer. The facial isomer is this. An octahedron has 8 faces, and if the chloros are aligned on one of those faces, the triangular faces, we call that the facial. And the means are aligned on another face, you know, versus the meridional. And the meridional, it just goes along the edge, the meridian of the octagon. That goes for both. So we have the facial meridional isomers here. Are these optically active? Well, the facial, I could just slice it right down the middle here, you know, between these two and right in the center there, and then slice this in half. I get two equal halves. This is not optically active. Is this one optically active? No, I just slice it down this plane, the two equal halves. Or you draw the mirror image and see, can you rotate it and make it match? And you can, you know, if you made the mirror image, the same thing. So, interestingly enough, like a square planar one like this, if we have 3 of a kind here, it's not optically active. Well, some people will say an isomer. What if I just put the chloro here instead and the amine here? Is that an isomer? No, because you just can rotate it and get the exact same thing. And so whatever you do, however you manipulate a molecule, it cannot match your reference molecule or your original molecule. Otherwise, if it matches, we don't call it an isomer. And so sometimes when I ask people to draw isomers, which I've done in the past, sometimes they'll get 20 of them because they'll just keep moving the atoms around and in every possible variation, but all those are the same thing as previous ones they had drawn. Over here, if we have two of a kind, then we got the cis-trans. If we have four, that are different, then we'll have different kinds of trans. Here, there's no isomerism, because these two aren't unique. This one you do there's a 90-degree rotation. Just rotate this 90 degrees off this amine here and the chlorose over here, and you have the exact same molecule. So when you're dealing with isomers, you're always thinking about rotation, like a 90-degree rotation, a 120-degree rotation, a 180-degree rotation, and then flipping along different axes. And so, you're better at this. And so here, if I draw the mirror image here, you see that these mirror images are superimposable. They're the same. But now what you have to do is you have to do these rotations in your mind. And so here we have the mirror image that we just made of this box. Is there a way we could rotate this so it matches this one? And so if we do a 180 rotation here, the blue ends up in the front. And so these are non-superimposable mirror images, which means they are optical isomers. So this is a word you want to know. You want to know geometric isomers and optical isomers and structural isomers. So we're going to have three types of isomers: structural, geometric, and optical. Now, geometric and optical share one thing in common. They all have the same bonds, just different three-dimensional arrangements of the bond. Sometimes it's very tricky to see, and this is one you're going to build. There's no cis-trans isomerism for this. This is tris-ethylene diamine, cobalt-3 ion. And so we have three bidentate ligands. This is like oxalato, right? Three bidentate ligands. Now there's no cis-trans here, because all bidentate ligands are adjacent to each other. They can't be opposite. Now, is this optically active? This is hard to see because it's not so easy to slice or dice. The easiest way to see this is to build the model. And so we make a mirror here and then build the model, or draw it on paper. And so if we draw it on paper, this is what we get. And then we try to do a rotation. So we'll go this axis and do a 180 rotation so that the ethylene diamine goes on the opposite end. And so if the ethylene diamine is now on the back, then you'll see that this ethylene diamine will be on this side rather than on the front side, on the back side. Do you see that? It's hard to see. And so this is what people do. People do, in organic chemistry, this is really important. The stereo chemistry is very important. And so this is what I saw at UCLA all the time. People would bring a stack of pencils and they'll start doing this, and then sing, building models. It says you aren't allowed, sometimes you're allowed models. They'll let you use models on exams. Sometimes they don't. So some people will use the pencils. I've seen other people tear pieces of paper to construct a little paper model of it to see. Other people can just look at it and visually rotate it in their mind. But it turns out that these are non-superimposable mirror images. This is optically active. So tris-ethylene diamine cobalt-3 is optically active. What does it mean to be optically active? It means that if one isomer has a bond on the front here and the other isomer has a bond in the back, that's going to interact with light differently. And so one way of thinking about it is, if one molecule has the bond here and the other has the bond on the opposite end, and you hit it with light, then the light's going to interact with this bond. Light does excite the electrons in the bond. And so it rotates the light this way, and the other molecule rotates it the other way. But what happens is, if one rotates it this way and the other rotates it that way, then they cancel each other out. When they cancel each other out, that's called a racemic mixture, and that is, it does not rotate polarized light. But what people are trying to do is they're trying to get, optically pure. That is, they only want one form. Like, if you buy ibuprofen, half of it's wasted because half of it is inactive biologically. The problem is that it's too hard to synthesize the active form without the inactive form, right? Because normally when you do a synthesis, you get a 50-50, it's collision, there's 50-50 chance it forms on the right, 50-50 chance it forms on the left. And so you always end up with a racemic mixture. And, that ends up being a huge waste of money, right? Huge waste of money because half of it's just thrown away. And so if you're making tons of it, you just wasted tons, right? And so in organic chemistry, what they're trying to do is they're trying to do stereoselective chemistry. So this is why, they're so into, orbitals and all this stuff, because how the orbitals interact is how you're going to generate a product, right? And if you can get it to only synthesize one form and not the other, you've just saved a ton of money. And so this is called stereoselective synthesis, which is a huge topic. So one way to do stereoselective synthesis is to use enzymes, or biological things, and then you'll have it. But otherwise, it's like wood versus, is that glycogen? Wood is made up of glucose, which is sugar, and glycogen is made up of glucose, which is sugar. But you can only digest glycogen because of the structure, but it's made up of the same. It has the same energy content. Termites can digest the wood. Yeah, they have different enzymes. But think about if you had a 50-50 mix of wood and glycogen. Half of it. Well, I guess fiber. It'd be high in fiber. Maybe it wouldn't be a complete waste, but the wood would necessarily. All right, so that's a isomers. Now we're going to move on to the second half of chapter 24, in part 2 here, and that's crystal field theory. These complexes have very interesting colors and magnetic properties. And so what crystal field theory does is it tries to describe or explain, the origin of the color and the magnetic properties in these complexes. Consider the bonding in a complex to be an electrostatic attraction between a positively charged nucleus and the electrons of the ligands. If we consider the bonding to be like that, then that bonding is kind of ionic, right? This is one of the reasons why, we leave the charges as is. So for example, normally when you form a chloro-metal bond, let's say a bond chlorine to cobalt, the cobalt's charge goes down 1, the chlorine's charge goes up 1, basically. In other words, we no longer said this is a chloride, this is a chloro, right? So cobalt was 3+, now it's going to be 2+. But we don't do that. We leave it as 3+, and we still call this minus, right? Leave it like that. And so in a way, we are already doing that. We're already calling that bonding ionic, although, when we form a metal ligand bond like this, we call it coordinate covalent. But anyway, I think this is not that important. What's important is this. Do the d electrons in cobalt, now how many d electrons does cobalt have? This is not the periodic table I want. Let's give it a different one. This is okay because this is a.
Let's see the shells section.
Let's say it's drops down.
This has the different numbering systems for the transition. I like the top row. Top row is the most useful, I think. And so cobalt is number 9. What does that mean? Well, actually, cobalt neutral has how many? Well, cobalt neutral is going to be argon 4s2, 3d 1, 2, 3, 4, 5, 6, 7. So neutral cobalt is electron configuration. Argon core 4s2, 3d 7. Cobalt 2 plus is what? Cobalt 2 plus, sometimes you see that. But cobalt 2 plus is a common charge. What's the electron configuration of cobalt 2 plus? Argon 3d7. Cobalt 2 plus is argon 3d7. In fact, 2 plus is a very common charge for all transition metals because of the valence electrons. How many valence electrons does cobalt have? Review. How many valence electrons does cobalt have? No, the cobalt neutral. 2 has 2 valence electrons, so plus 2 is a very common charge for cobalt. These d electrons are considered core electrons, but it's not like a filled core, and so those can be reactive as well. And so when we go to cobalt 2 plus, we've just lost those 4s2, we're down to 3d7. Okay. This is why I like this numbering system up here, because if I want the electron configuration for cobalt, this is how I get it. I go cobalt plus 1, cobalt plus 2. What number am I at? 7. So cobalt plus 2 is D7. D7 is important because D7 is where the color and the magnetic properties are going to originate from, is the number of D electrons. Now, do those D electrons participate in the bonding? Well, actually, before I do that, maybe we'll get some more practice. We're going to get more practice with this. Cobalt plus 3. What is it?
3d6.
3d6. Nickel plus 2. 3d8. Or we just call it d8. d8. Copper plus 1. Copper plus 1. Copper plus 1 is plus 1, D10. Copper plus 1 is D10. Copper plus 2, D9. Zinc plus 2, D10. D10 is a filled subshell, right? So it's fairly stable. So zinc, do you ever see zinc 3 plus? No, because the D10 is hard to break apart. The zinc 2 plus is its only charge. Cadmium only has 1 charge. What is it? Plus 2, D10. Silver only has 1 charge. Plus 1 is D10. Right? Those valence electrons gone. Copper has 2 charges, and the most common one isn't plus 1. The most common one is D9. It's copper 2 plus. And so why is that? Why did I just break apart that filled subshell? Because it's a D10 subshell. And the reason is because of crystal field theory. That D9 electron configuration is stabilized by crystal field theory. And so that's the reason why. Well, why doesn't silver do it? Because Well, because of the electronic environment and the energies of the orbitals, it just doesn't profit in the same way that copper does for this. Gold, +1 and +3 are common. But one thing, when you get to higher and higher energy levels, what happens to the spacing between the sublevels? It shrinks smaller and smaller. And so pretty soon, when you get to higher energy levels, we have a lot more exceptions where, part of the D subshell fills and then part of the F subshell fills at the same time. Not completely, because the energy gap is very small. Pretty soon just thermal energy is enough to do it. And so that's what happens. Okay, now, so we want to get, good at this. Titanium +4. Titanium +4 is probably the most common charge on titanium. What is titanium +4? Just argon, right? D0.
What is that on titanium?
I'm sorry, I couldn't hear
How many
you.
valence electrons does it have?
Titanium only has 2 valence electrons. Titanium forms +2.
That's what it's stable is.
So +2, you lose those. Titanium also forms +3. +3, you lose one of the D's. And titanium +4 is where it stops. Titanium +4 is just the argon.
There's too much energy.
Configuration. Scandium only forms 1 charge. Yttrium and scandium only form 1 charge. These are fixed charge. What's the fixed charge on scandium ion? Not +1, +3. Scandium's always +3, yttrium's always +3. Okay. All right, so first we need to figure out how many d electrons. Then we need to figure out what's going on with the d electrons. So if I have some complex like this, some amine complex, let's say cobalt +3, I have 6 d electrons. So what should I do with the 6 d electrons? 1, 2, 3, 4, 5, 6? Is that what I should do? What should I do? Or do these electrons participate in the bonding? What's a ligand? A ligand donates how many electrons? Can these electrons participate in the bonding? A ligand comes in like amine. Amine's going to donate how many electrons? 2. Well, what about all these electrons here? Already there. What do we do with those? Do we even show those electrons? No. No. The d electrons aren't shown. Right? We don't do this. We just say the cobalt 3+, we have an amine come in here and bond to it. And then we form a coordinate covalent bond. Like this, right? And so the d electrons are what we call non-bonding electrons. Non-bonding electron. Non-bonding electron. And so these don't participate. These are non-bonding. They stay on the inner shell. Just stay there. We describe the bonding of transition metal complexes using MO theory. We do not use valence bond theory. Otherwise, what are you going to do with Vesper and all that other stuff? Kind of. Yeah. And Vesper doesn't even work, because how do square planar complexes form? So Vesper fails. And therefore, valence bond theory fails. Okay. But do you think these electrons are happy that more electrons are coming in here? No. You know, because these electrons are negatively charged, and what makes a good ligand? Negative charge density. So what happens is these electrons are not happy. These electrons become destabilized. That is, there's repulsions that are going on. And so let's take a look at the repulsions here. As a way you can imagine it. Those are d electrons. Do you guys remember the shapes of the d orbitals? These are the yellow ones are the d orbitals. We have the dz squared here, which has this little hula hoop, and the dx squared minus y squared, which has 4 lobes on the x and y axis. We have the dxy, which is in the xy plane, and with the lobes between the axes. The dxz, which is in the xz plane, with lobes between, and the dy squared. No, this is wrong. It's the dx squared minus y squared. The dx squared minus y squared has the lobes directly on the axes. Oh, no, that is it.
Yeah.
Oh, okay.
trying to
We
show
have the
offset.
dx squared minus y squared with lobes directly on the axis. This should not be dy squared. Tell me what this should be. It kind of looks like a 2, but not really a 2. This is the dyz orbital. So I guess just a typo there. This is dyz. We have the xy plane, the xz plane. The only plane we're missing is the yz plane. And so that's the dyz orbital. All right, now imagine having electrons in these orbitals. They don't show the electrons in the orbitals, but we have electrons in the orbitals here. And along comes a ligand. The ligand we're going to imagine as this blue negatively charged ball. If this blue negatively charged ball comes in, then there are going to be repulsions because there are electrons in the orbitals and electrons coming in. What's pulling in the ligands? Well, the central metal. The central metal is positively charged. But these electrons here aren't going to be happy. Some are going to be less happy than others. Which of these orbitals will be the unhappiest orbitals to see these new neighbors come in? If you're one of those yellow orbitals, which one would be the least happy to see these new neighbors? I'd say the x squared minus y squared would be the least happy because look at these ligands are coming along the axes. Plus x, plus y, minus y. That's because of the way we set up the coordinate system. But once we set it up like this, then we can reference to the others. These ones won't be as unhappy because you see the ligands are coming between the lobes, not directly on the lobes. And so this one's okay, but still there's going to be repulsions. This one's quite unhappy. How about the dz squared? Yeah, this one's going to be quite unhappy too because it has the lobes on the z plus z minus z, but it has this hula hoop, which is going to be unhappy in the xy plane. And so what does that do? Well, it changes the energy of these. And so what we have here is this. First, with the free metal, no ligands, you know, the orbitals are happy. There are 5 orbitals here. I don't know why they have so many lines. There should just be 5 lines. And then if you bring in negative charge density, like a spherical negative charge density, then there's repulsions. But some of these are repelled more than others. The dz squared and the dx squared minus y squared are more significantly repelled, whereas the dxy, dxz, and dyz are less repelled. The energy increase here has to equal the energy decrease. You know, we have 5 orbitals, so 2 have to pop up higher in energy and 3 pop down a little bit lower in energy. But do you see the energy of the d orbitals are no longer degenerate? And so we've lost the degeneracy because of the ligands coming in. It's called an octahedral field. And so this is just with spherical field. This is with an octahedral field ligands. And the splitting of the energy is called delta. Delta stands for the crystal field splitting energy. And this little O here stands for octahedral field of ligands. And so crystal field splitting, in other words, it's just a field of ligands coming in and interfering with the orbitals. If we have the same coordinate system, we can bring in the ligands for a tetrahedral complex. The ligands for a tetrahedral complex are going to come, between, right in the middle of the y-x-z axis, right in the center there. And so it's going to interfere with the orbitals in between the lobes, whereas in between the axes. Whereas along the axis, there are no ligands coming in. And so for tetrahedral field, it's flipped. Now the orbitals that have lobes between the axes are repelled more than the ones along the axes. And so this is an inverted pattern. It's an inverted pattern. And the other thing is the splitting is not as strong. For the same negative charge density, it's only about 2/10. What is it, 4/10? Something, 2/5. Yeah, like 44% of that is the octahedral.
You always represent in reference to the octahedral?
Yeah.
Or is that just an accent?
No, it's just the splitting's small. The splitting is going to have an impact on magnetic properties, the degree of splitting. That's for tetrahedral. This is for square planar. If we bring in a square planar arrangement of ligands, they're going to be along the axes. And so this is really going to screw up the x squared minus y squared badly. And so you see the x squared minus y squared is really split badly. And then the xy because it has lobes in the xy plane. And then the z squared because it has a little hula hoop. And then the xz and the yz. And so we get this kind of splitting pattern. And so it depends on the field, octahedral versus tetrahedral versus square planar. Those are the splitting patterns that we see. Now, the strength of the ligand is going to have an impact. It's going to change the delta, Strong field ligands like cyanide, nitrite, ethylene diamine, pyridine, amine, EDTA. Strong field ligands will have strong repulsions, which leads to big splittings. Weak field ligands, called chloro, bromo, iodo, have weak electric field interactions, and small delta. And so here, if we put in one of these ligands, the splitting grows bigger. If we put in one of these ligands, the splitting goes smaller. The way people memorize this is they don't memorize the individual ligands, they just memorize this, the donor atom. As a cyanide is a carbon donor. Nitra, N, ethylene diamine, pyridine, amine are nitrogen donors. EDTA is an oxygen donor. Water is an oxygen donor. Thiocyanate is a nitrogen donor, but ignore it because it doesn't fit the pattern. So there's exceptions, let's say. Oxygen donor, oxygen donor, oxygen donor, and then halogens. So the way we memorize this is it goes carbon donor is the strongest, followed by nitrogen donor, followed by oxygen donor, followed by halogen. So the impact is how big it splits. And so this is a halogen. Halogen doesn't split very much. And so we call it weak field. So this is a weak field ligand. Amine is a nitrogen donor. It's a strong field, so it splits it. Much bigger repulsions here. Strong field, bigger splitting. So that has an impact on how we fill this with electrons, because cobalt-3, how many D electrons does cobalt-3 have? We just did it over here. D6, right? So cobalt-3 is D6, so let's plug in the electron. Normally this is, you remember the off-bow principle. Off-bow principle is fill the lowest energy first, and then go to the higher energies. And so normally we'd fill it like this, 1, 2, you remember Hund's rule? Yeah, 1, 2, 3, then pair, 4, 5, 6. This is what we call a diamagnetic complex. But it turns out that if the splitting is small, then there's a trade-off. There's a trade-off between promotion energy, that is the splitting energy here, delta, versus the pairing energy. When we pair two electrons in a single orbital, there's repulsions. And so over here, delta is big compared to the pairing energy, therefore the pair. Here, the pairing energy is bigger than delta, so it's easier just to promote it. And so the way we fill this is 1, 2, 3, and then jump up, because we'd rather promote it than pair it. 4, 5, and then we got a pair. And so it's better to pair a lower energy one. And so hexafluoro, cobaltate 3, versus hexamine, cobalt 3 are going to have different magnetic properties. This one's going to be diamagnetic. This one's going to be highly paramagnetic because of unpaired electrons. And so the magnetic properties are totally different. And also, they're going to have different colors because it turns out that delta is typically about visible energy in magnitude. That is, if I shine a photon here, I can promote an electron from this lower energy d orbital to this higher energy d orbital and absorb visible light, giving this a color. And so typically the way we understand these is this. What we call strong field ligands, actually let me back up a step. Strong field ligands are called low spin complexes because the spin number is low. There's not many unpaired spins. Whereas weak field ligands are what we call high spin complexes because we have a greater number of unpaired spins. So that's magnetic properties. High spin, more unpaired electrons, low spin, fewer unpaired electrons. Now color is another thing. This is going to absorb higher energy light or lower energy light from this. This absorbs higher energy light. And so this is going to absorb like a blue photon or violet photon. If it absorbs a blue photon, what color is it? It's the opposite. It's the complementary. That's the what's opposite of blue? Yeah, something like that. And so if this absorbs high energy light, it appears to the eye as a low energy color. And so these kind of complexes with amine, cyano are going to look like red, orange, yellow, green, right? Whereas these complexes here, which absorb red, orange, yellow, green, are going to appear the opposite, which will be violet, blue, green. And so these kind of complexes are going to look higher energy color. These are going to look lower energy colbut why do you say green twice and lower? Yes, it's in the middle.
Because it's like the thirds that you're trying to get across afterwards.
All right, with tetrahedral, the interaction is just weak. And so all tetrahedral complexes are high spin because delta is small no matter what ligand you have on there. And so even if I put cyano on there, which is the strongest ligand, cyano, the splitting is bigger, but it's not big enough. And so all tetrahedral complexes are high spin. Now the color is going to change, depending on the ligand that we put on there. All square planar complexes are low spin. So what does it mean? High spin means promote before pairing. Low spin means pair before promoting. And so square planar is low spin, more paired electrons. So here's the color wheel. So let's take a look and see if our predictions. Color is always, it's difficult too, but something like aqua. Aqua would be on the lower end or the higher end. Would it be a strong ligand or a weak ligand? We call it field ligand. Strong field ligand or weak field ligand. Aqua. It's right in the middle, right? Nitrogen, carbon. It goes carbon, nitrogen, oxygen, halogen. So it's kind of on the lower end, maybe. Amine has nitrogen. There's the nitrogen donors, amine. And so you see, look at the color. It's violet. And sometimes it's mixed up because you have a mix of ligands on there. And so you can just see the color varies. Magnetic properties can also vary. Here you can see different colors here. Okay. Yeah. All right, actually that wasn't, there's one other section of this which I didn't really talk about. And I'm not really going to talk much about. And that is when we, if you look at this, this is just forming a complex, you know, Zn2 plus 4 mean. This is, we call this K, what do we call this? KF. That's a KF equation. But, you know, KF, that's a net reaction. It actually occurs one ligand at a time. And so we get K1, K2, K3, K4. But we did combine. Can we use the combined method, or do we have to use the stepwise method, or do we have to use the simultaneous method? We just automatically went to combine for this, right? And the combined works for this because if you look at the series of successive steps, this is another case where combined will work. You know, they're all, the K's are all big, meaning that each product will be converted in the next one, which will be converted in the next one. And so it's this chain reaction that you're just going to end up at the end. And so the combined method works for this, even though it's multi-step. And so if the combined method works, well, we might as well not even bother talking about stepwise or any of that stuff, right? Might as well just go straight to combine. And so we don't do the stepwise for this at all. And so you can see the combined there. Now, actually, one more section here. But I talked about this very briefly, and that is, you know, iron 3 is acidic, or actually even more acidic than acetic acid. Do you remember us talking about this? Yeah. It's because of the, what we call the inductive effect. You know, iron 3 plus is a strong electron withdrawer, which is going to make water much more. The water as a ligand is much more polar than water itself. And as we saw in the lab, increasing the polarity increases the acidity, right? And so that's iron 3. Iron 3 actually is a polyprotic acid. There's a Ka1, 10 to the minus 4. There's Ka2, 10 to the minus 4. Ka3. Ka3 takes it to iron 3 hydroxide. It's not shown here. The charge is wrong. These equations are wrong. But this would be, you know, I didn't do this because this is, you know, step 1 is 10 to the minus 4, step 2 is 10 to the minus 4. You know, this is going to be simultaneous. Oh, one more section here.
We got 12 slides.
At the bottom it tells you how many more slides you got.
All right. This is what we call, you know, chemical exchange. How easy is it to break off that ligand? Sometimes it's easy to break off a ligand. If it's easy to break off a ligand, we call it labile. If it's hard to break off a ligand, we call it inert. And so there are labile complexes and inert complexes. This I'm not going to test you on. And the other stuff I'm not really going to test you on. But these are, here's labile complexes, just means the ligands are easy to break off. Inert complexes, the ligands are really hard to break off. So something like EDTA would be inert. That's really hard to break off, chelating agents. You aren't going to be tested on this either, but if you want to read more about cisplatin, they talk about it. We talked about stabilizing oxidation states. Cobalt-3 is unstable in water. Cobalt-3 will oxidize water, but if you complex it with amine, it's stable. We talked about this in regards to aqua regia, royal water. Photography, qualitative analysis. I think we did this one, the SCN complex, the red one for iron detection, didn't we?
Stop bleeding iron.
Yeah. Sequestering metals using EDTA. Here's a cobalt EDTA complex. Is EDTA cobalt complex optically active?
No.
Yes, it is. There's two ways that the EDTA can attach.
Oh, it's up there.
They're non-superimposable mirror images. These are non-superimposable mirror images. Biological applications. Porphyrins are very common. So the chlorophyll has magnesium. This is the active center of chlorophyll here. And that's it. I have your tests also, but I need